Hey there, and welcome back to our next lesson on Foundation Mathematics, Algebra. So we are taking a look at simultaneous equations today. So I've mentioned this before. We saw back in the very first lesson on algebra when we have an equation of two variables or more, but we only really deal with ones with two. Um, it's impossible to really solve them and get a specific solution to that equation when you've just got that one equation of two variables. Like we've seen last time with graphs, we can plot the equation. You see there's essentially like an infinite number of solutions along that line. Every point along that line is a solution. And we've seen, okay, if we have an additional piece of information, typically in the form of another equation, which could have a different line, the intersection of those two lines marks then a single point when they're both true, and then that gets us a specific value. So that's what we're going to be looking at, is when we have two equations and we solve them simultaneously to get one specific solution, which is basically a value of x and y. Say if we two variables are x and y, such where the both equations are true at the same time with those. So okay, so we'll quickly take a look at that graphical interpretation again first. Then we're going to look at how we solve simultaneous linear equations, because that's only really um, the case that you'll get at foundation level. You won't be asked to solve, non-linear equations. And then we're going to look finally, which is a common thing you'll get when it comes to uh, simultaneous equations, where we get given some information in text and we need to basically extract the key information to form equations out of that and then use simultaneous equation techniques to solve it. So we're going to look at how that works, these kind of more worded problems, which I know can be challenging for some. So let's look at the graphical interpretation first. We've already seen this a little bit before. Say if we have a graph and we a set of axes and we plot a graph on those axes, this quadratic graph that we have here, and we know we can generate a whole bunch of points like this, and none of these points are solutions to this equation because they're not on that line. Whereas if we took a whole bunch of points like this, these are all solutions to uh, that equation. And you could always test that for yourself if you took some of those points that I've shown there and try plugging them into this equation. You'll see these ones that will come out equal, whereas the points I showed before won't. So if we have another equation with its own line, like this case, it's a linear one, it's the same thing. All the points along this line represent, solutions to that equation. And so these 2 points here would then represent solutions to both of these equations at the same time. So the coordinates of those. So we could always try and read off those coordinates if we want, and we'd get an estimate. You see here in this case we get two solutions because it's a quadratic and a linear equation. So you could get something like this where you want to read it off from a graph, but actually solving them mathematically, like two simultaneous equations. Like I said, you only get two linear ones. Um, so those two coordinates, you read off the x and y values, you could try plugging them into both of those equations there, and you'll find both of them will come out true, or at least close to true. There might be a slight error if you can't read them off exactly. So that's the graphical interpretation of solving simultaneous equations. So now we're looking at actually solving simultaneous linear equations. And there's two methods we look at. The first one being the elimination method, where we essentially use one equation to eliminate one of the variables in the previous equation, in the other equation. And that then has the effect of reducing the problem down to an equation of only one variable, which we know how to solve. Even if it were a quadratic, but we won't get quadratics in this case. It's just going to be linear ones, which we definitely know how to solve. A linear equation of only one variable, we can do that. So that's what we're trying to do. So here's an example, and this is an example of putting a linear equation, say, in a different form to like what we saw before. Like we saw last time when we was working with graphs, we generally want it in the form of y equals mx plus c, where we have y as the subject, and then you got your x term and your constant term on the other side, and then we can read off the gradient being m and the y-intercept being c. That's really handy for graphing. For simultaneous equations, generally we want to put it into this form, so it's just rearranging things a bit, where we've got our x term, our y term equals to our constant term. and we put both of them into that form. And what it does, it puts things into nice, neat columns. You see, we've got our x terms, we've got our y terms, then we've got our constant terms. And you'll see in a second why that's useful. What we need to do is try and eliminate the variables by doing like a combination of the two equations. And how we do that, first of all, we want to change one or perhaps both of them. Sometimes we'll see that in a sec. What we might have to change both of them. In this case, we can just change one of the equation such that one of the terms, the x or y terms, will match. So in this case, what we could do is we could multiply that second equation by 3. And you might notice if we do that, we're going to essentially get 6x plus 18y equals 42. And what we've managed to do there is get the x terms to match, where we've got a 6x and a 6x, or perhaps you could have a 6x and a minus 6x. We'll see, that can work too. And when they match like this, what we do is we're kind of doing something that it kind of might look like long arithmetic, like here, if we do a subtraction of the two. And back in all the way back in lesson 1 of numbers, where we were doing long arithmetic, and it's like you could read down the place values and do each number individually, like units, your tens, your hundreds. It's kind of like the same thing here once we've got into this form, and we could kind of do the subtraction down each column. So, and you'd essentially get this. Because, okay, so we're doing 6x minus 6x, so that just cancels out. It disappears entirely, which is what we wanted to happen. Then we do the 3y minus the 18y, gets minus 15y. And then we do the 12 minus the 42, gets minus 30. And that is something we can do. What we're essentially doing, you've got two equations here. You've got a left-hand side and a right-hand side of each. And if the left-hand side is equal to the right-hand side, which is basically what an equation is, well, we could do the left-hand side of one equation minus the left-hand side of the other equation will then necessarily equal to the right-hand side of the first equation minus the right-hand side of the second equation. You think about that logically, it makes sense that would happen. And so that's why we could subtract down the columns like this. You're essentially, subtracting one, the left-hand sides and then the right-hand sides, collecting like terms and the sort. But this just gives us a nice, easy to visualize way of doing it when we get our terms, our different types of terms in nice neat columns like this. So that's the elimination method. That is the key trick that we need to do there, where we change one of the, like, scale one of the equations by multiplying through by some numbers such that the coefficients of one of the terms will match, in this case the x term. Then we subtract down the columns like this, so that term will cancel out. We've now got a little equation of just one variable, y. And if we divide both sides by minus 15 here, we're going to get y equals 2. And that's the hard bit done, because now we could go back to one of our equations, like say this one, any equation that we have of x and y here, because they're all essentially, they will all work. Because we've got the two original equations, which are, we're trying to find when they're both simultaneously true, and any scalings of that we do, it's still essentially the same equation. It's kind of like with a fraction, when you scale the top and bottom of a fraction, like 2 over 3, you might multiply the top and bottom by 5, say, to become 10 over 15. Even though the numbers are different, it's still essentially the same fraction, isn't it? The same proportion. And it's the same thing here with an equation. If you multiply through by a particular number, the general relationship between x and y hasn't changed. It's still the same equation. It's kind of like, you can think of it in very much the same way. So at this point, we can basically just take any equation that we have of x and y, and we already know what y is at this point. We know these two are going to be simultaneously true when y is equal to 2, because we used both of those equations there, by doing a combination of the two to get that new equation of y that we could solve to get 2. So that they're both simultaneously true when y is 2. Now we're just trying to find the corresponding x. So we can take that 2, substitute it into any equation like what we've got here, and now we've got, again, an equation of only one variable with x this time. So 6x plus 6 is 12. So 6x equals 6 if we subtract 6 from both sides, and then x must be 1 because we divide both sides by 6. So that bit at the end is always going to be the same. You just, you can substitute in the variable you've already found, and then you can easily get an equation of the remaining variable to solve. It's that first step when you've got the two equations of two variables. We need to eliminate one of them. And from our graphical understanding of simultaneous equations, we could tell that this intersects at the point 1, 2 on a graph. Without even drawing the graph, we know this is going to be their intersection point, because that's what it means. So let's take a look at another example. So we're looking at elimination method again. Like I said, we've got another method we'll look at in a sec. I'm looking at a more complicated case this time, because you see there that one was quite nice, where we just had to multiply one of the equations through by 3, and then the coefficients match up nicely. But you see here, we can't really do that. Like, there's nothing we could really multiply that first equation through, say, to change 14 into 21, or 9, like the coefficient of 9 on the y, to turn that into 11. It would be like a fractional value, which we could do. And it would work. It'd be a bit more complicated. So in cases like this, typically we need to change both equations to get one coefficients to match. And in this case, there's multiple ways you can do it. But you want to pick the way that's going to be easiest. Like if we try and get the y coefficients to match, 9 and 11, the only way we could do that is essentially multiplying the first equation through by 11 and the second equation through by 9, because 11 and 9, they have no common factors. You essentially, if we did that, you'd then get 99y in both equations, and then you could eliminate in the same way we did before. But a lot of these numbers are going to get very large, and we want to try and keep them smaller where possible. So what we could do is try and look for ones that do share common factors. And in the first one, like if we look at the coefficients of x, look at the coefficients of x, 14 and 21, you can see they share a common factor of 7, quite a large factor as well, relative to those numbers. So what we could do, right, we don't want to times the second one through by 14 and the first one through by 21. That'd be even worse. But what we want to do is we want to times them both by a number such that those x coefficients will match. And so we want a multiple of, we want just a number that is going to be a multiple of 14 and a multiple of 21, but we want the smallest possible multiple. Well, we've done that before. Like you might already be, sort of recognizing what we need to do here. What we need is the lowest common multiple of those two numbers. Like you see, the lowest common multiple of 9 and 11 is just going to be 99, 9 times 11, because they don't share factors. But 14 and 21, it's not going to be 14 times 21. It's going to be 42. Because you see 14 times 3 gets you 42, and 21 times 2 gets you 42. So you see there, if we times the first equation through by 3 and the second one through by 2, that x coefficient will match. So you see there that we've seen this a few times now, where things like lowest common multiple can really come in handy. They go beyond just, prime factorizations and things like that we learned before. You can even apply them here to then try and find the simplest way to solve a problem like this, so that the numbers don't become huge. So let's do this now. If you times that, you might want to try this yourself first. If you times that first equation through by 3 and the second one through by 2, you'll get this. So I've just gone through and you're just basically multiplying all the numbers through by 2, multiplying both sides of the equations by 3 and 2 respectively, like the two equations, and we get this. And you see both, as expected, the x coefficients match, which is precisely what we want. Now we can do that subtraction, and you see it all kind of comes down quite simply. 42x minus 42x is going to disappear. Good, that's what we wanted to happen. 27y minus 22y gets a 5y. 288 minus 268 leaves us with 20. And so we've got this simple little expression, equation. 5y equals 20, therefore y equals 4. You could divide both sides by 5. And as usual, that's the tricky part done. Now you can just pick any equation, preferably not these two, where we've scaled up all the numbers. We go back to one of the original equations, like we had 4x plus 9y equals 96. We can substitute in that value of y equals 4 now. So we've got 4x plus 9 times 4 equals 96. So 9 times 4 is 36. So we've got 14x equals 96 minus 36, which is equal to 60. And finally, we can then, if we divide both sides by 14, we're going to get x equals 60 over 14, which we can simplify to 30 over 7. So yeah, you can quite often come to fractional solutions like that. You need to make sure you're comfortable with that and working in fractions, simplifying fractions, that sort of thing. So there you go. That's the elimination method. So we've got like a simple case and then a more complicated case here. But you see, it's the same thing. You need to scale up one or both of your equations in some way, such that the coefficients of one, either the x or the y term, match. Perhaps using lowest common multiple here. If you're not if you can't remember how we work out lowest common multiple, you can look back at the lesson on prime numbers that we did a while ago. Although here, where the numbers are relatively small, like 14 and 21, with a few guesses, you can probably find a multiple of those two that is, the least possible. So now let's move on to the second method, the substitution method. So this is a different method which is handy in particular situations, especially when working with solving simultaneous nonlinear equations. I mean, there are some cases where you could only solve it through substitution and not through elimination method. So it's very important. But like I said, you don't have to worry too much about that because you won't be working with non-linear simultaneous equations. You only have linear ones. But there's still, within the context of linear equations, there's still times when the substitution method does work better. Say something like this. So when we've got, say, an equation where one of the variables is the subject of the equation. So you see that first equation we have there, x equals 2y plus 5. You see x is the subject. If you ever get a question that maybe it's not like in this form but it's still asking you to solve it through the substitution method because that's the skill it's trying to test, then you need to rearrange it so it's one of the variables is the subject like this. But yeah, if we've got one given like this, and maybe you get the choice of whatever method you want to use, substitution method can work quite well here. And the reason for that is because when we have an equation with one of the variables as the subject, we're based like here, we've got x written in terms of y. So in the second equation, where we've got 3x plus 4y equals 20, wherever there's an x, we could just basically put in 2y plus 5 instead, like this. So you see there, I've got 3 times by 2y plus 5, and then add 4y equals 20. So you see, I've just taken that expression for x in terms of y and popped it in where the x was. Now, okay, this might look like quite, a little bit of a complicated equation, but the key thing is look that there is only dependence on y here. There's no x. This equation is an equation of just the one variable y, and so we know we can solve this. That's the main thing. So if we go through the steps, if we try, okay, first of all, say let's expand out those brackets and collect together like terms. So we've got 3 times 2y, which is 6y, plus the 4y we have there as well, gets us 10y. And then we're doing 3 times the 5, which is 15. So I'm kind of doing a couple of steps there. If that's not clear what's happening, then you might want to pause and just work that out yourself quick using the techniques we've seen with brackets and that and collecting like terms. Then now we've got a very simple equation. We've solved a million of these by now. We can find y is equal to half. If we subtract 15 from both sides, we get 10y equals 5. Therefore, y equals 5 over 10, which is 1 over 2 if we simplify. So now, again, you've got to be comfortable with your fractions. Because, okay, we've got a fractional answer here, but we need to substitute this back into one of our equations. When doing the substitution method, pretty much all the time, you want to substitute back into that equation where we have x as the subject. It's just the easiest. We've got like an actual formula here for x in terms of y. So it just makes sense to substitute back into that one. Although you technically could substitute in the other one as well. You'd get the same answer. It's just you're making it make a bit more work for yourself. It makes sense to substitute back into that one for the y. So, okay, we've got x equals 2 times a half plus 5. 2 times a half is just going to be 1, isn't it? So x equals 6. 1 plus 5. So there we go. We get the solution using the substitution method. So that's what the substitution method is where you get one of the equations. You've written it as one variable is the subject, in terms of the other variable, and then that's it. Now you've got an expression of that one variable in terms of the other variable. You can take that expression and put that in the other equation. So here we've got 3 times x. So that would be basically 3 times 2y plus 5 in brackets. So you got to be careful of that. You got to make sure it's times in the whole thing. And then there you go. Got an equation of one variable, solve, and then once you found the first one, you can easily find the second one. So let's look at finally forming equations. So that's when you might have something like this, like quite a wordy question. So these can be sort of more tricky problems. We've got to try and extract a couple of equations out of this, and then we can solve those equations. And this is really good technique because this is what algebra is all about. We take real life scenarios and we, quantify it. And we get it written down as like an equation, and then we use all these like general techniques that we're using for algebra to then solve those equations. So here's an example where we've got this person, Alex, invests in 2 accounts, and these 2 accounts have 2 different interest rates. One where you're making 5% per year, the other one's making 3% per year. He's invested X amount in account A and Y amount of money in account B, and we're told he earned a total amount of interest of £220 in the year from a total of £15,000 of investments. Okay, how much must he have invested in each of the accounts? So, okay, there's a lot going on there. So what we're trying to work out is how much he invested in each of the accounts. So those are going to be our 2 unknowns that we're trying to find, our X and Y, which they've already given to us in the question here, that he invested X amount in account A and Y amount in account B. If it didn't say that, okay, well, that's what we're trying to work out. So you label those as your 2 unknowns. So that's the first thing you need to do when forming an equation. What are the unknowns? What are the unknowns that you're going to be trying to find? So, and now try and form equations. So first things first, we've been told that the total amount of investment made is £5,000. Therefore, x plus y must be 5,000. So there's equation 1. Okay, that's equation 1, our first sort of constraint on this system. The second equation is a little bit more complicated. So we would use, say, the other information, which is about the interest. We know the total amount of interest he earned was £220. Okay, what would that be in terms of X and Y? Well, we know he made he makes 5% of interest on account A, 3% on account B. Therefore, 5% of X plus 3% of Y would equal 220. As an equation, we could put that like this. Those percentages we might want to put as a fraction. 5 out of 100, 3 out of 100. And so we've got a second equation here, which we can then try and clean up a little bit because those fractions aren't very nice to have. So say if we multiply everything through by 100, we'll get 5x plus 3y is equal to 220 times 100, which is 22,000. Okay, so you see there, we've used all the information that was given us in the question. So we know there's nothing else really we can take into account. And we've got 2 equations now, 2 variables. So again, you can solve this now because we can't solve one equation of 2 variables. We can solve it if we've got 2 equations of 2 variables. So now we just solve this using whatever method we want. We've got an x plus y equals 5,000. We could maybe rearrange that to make x the subject or y the subject. I've chosen to go ahead with the elimination method, which is the one you'll encounter more often, really. It's foundation. So you want to make sure you're quite strong on that one. That first equation, I could multiply that through by 3 like this to get 3x plus 3y is equal to 15,000. And so this time I'm eliminating the y variable because you see those are the ones that are matching. So if I do a subtraction, but I'm kind of subtracting the other way to avoid a negative number here. Rather than doing 3x minus 5x, I'll do 5x minus 3x, which gets me 2x. 3y minus 3y gets me 0. That just cancels out. And then I've got 22,000 minus 15,000. So I'm doing the second equation, subtract the first equation. So I get 2x equals 7,000. So x is 3,500. And as usual, once you found the first one, the second one's quite straightforward to find because we know they both add up to 15,000 in this case. sorry, we know both amounts add up to 5,000. So 3,500, the second one must be 1,500 in order to come up to 5,000. So we must have invested 3,500 in account A and 1,500 in account B in order for these numbers to, to make sense. So that's an example of a real problem using like a worded problem where we have to extract equations out and then we solve those equations and we can find this previously unknown information. Now, we could take another example like this, which could be more of a geometric one. Okay, so we haven't done too much on geometry yet, but you probably already know that the area of a rectangle is essentially the multiplication of its two side lengths. But you see here, we've got these side lengths in terms of unknown amounts. We've got X and Y. We've even got an A there, but we're actually been given three. There's more than just two pieces of information in this, so we can work out these three variables. The simplest one we could work out is, say, area, because the area we know is basically the two side lengths times each other. So it could be like 8A equals to 88. 8 times the A gets 88. So that's the simple one to work out what A is right off the bat. We've got A equals 11. Other equations we could do are equating opposite sides of the rectangle, because we know opposite sides are going to equal to one another. So you get 2x plus y equals A, which we've already found out to be 11. And we've got 3y minus 4x is equal to 8. So you might get things like this where you've got like a geometric problem and it requires you to then use the properties of that shape to then deduce equations like this and then try and solve those equations. And at foundation level, you won't get anything terribly difficult. It'll be typically like a rectangle like this. You won't get really complex shapes or anything. But you see here, we managed to find out what the A is pretty quickly by using the area. Now we've got these equations of X and Y, pair of simultaneous equations again, which we can quite easily solve. So what we can do is, first of all, that first equation I've multiplied through by 2. You see 2x plus y equals 11. I get 4x plus 2y equals 22 by multiplying that through by 2. And you see now the x terms match. They're not 4x and 4x. We've got 4x and minus 4x. So if I want to combine these together into in such a way where that term's going to cancel out, what we need to do is add them this time. We're going to like this. And you see here, we haven't got all the x, the y, and the constants in nice neat columns, like the x and the y are the other way around. You don't strictly need to. Like once you've got some practice with this and you get how this works, you're adding the left-hand sides and adding the right-hand side. So as long as they're on the right-hand side, the correct hand side of the equation, it works the same way. But if you prefer, you can just rearrange things. Like we know how to rearrange things like terms of equation, don't we? Like that second equation, we could make it minus 4x plus 3y equals 8. And then you would have things in nice neat columns. But either way, you add them together like this. You see the 4x minus 4x will cancel out. 3y plus 2y will get you 5y. On the right hand side, we've got 22 plus 8 gets us 30. Therefore, y is equal to 6, because we just divide both sides by 5 at that point. And now finally, we take that value, we can substitute it into any one of our equations we had. I'll take this one, whatever one's simplest really, because like I said, all of them are going to work because they're all essentially, relating to the same solution. So we get 2x plus y equals 11 is one we had before, equating the two vertical sides of the rectangle. Y is 6, so we've got 2x plus 6 is 11, and then this we can just go through and solve. We get 2x equals 5, and therefore x is equal to 5 over 2. And there you go. So those are some more tricky examples. But that's the end of this lesson. I'm going to leave you with a bit of a challenge question today, as opposed to a fun fact. So take a look at these two pairs of simultaneous equations we've got. So they're two different problems to be solved. And if you try and solve these, what you'll find is they get very peculiar solutions. And have a think, like try and solve them and have a think of why you get those solutions. And perhaps you might want to try plotting them, plot them yourself on a graph, or you can use some kind of online graphical calculator. Like I'd like to use this one called Desmos, Desmos. It's really good where you can type in various equations and it'll plot it for you. And take a look at it, and maybe that will help you understand why you get the solutions you do. But yeah, there's a couple of interesting cases there, which you're not likely to get in an exam unless they're trying to, trick you in some way. But it's good to understand these because they, to help really cement, your knowledge of simultaneous equations and the relationships to graphs. So here you go. Here's the takeaways for today's lessons. Key things you need to know. And next time is going to be our final lesson on algebra. So yeah, we've been doing algebra for a while now, quite a few lessons. Big topic, algebra. So we're going to be looking at sequences. We're going to take a look at what those are and what we can do with them. And after that, done with algebra, and we'll be moving on to geometry. So I'll see you next time for our final lesson on algebra.